All right. Welcome everyone. Today we host Seok-Jun Chang as a speaker on his recent interesting theoretical paper in little red dots. He's a postdoc at MPA, and he will talk about his radiative transfer modeling to reproduce Balmer lines in little red dots. And welcome him and yeah. Thank you.
Okay. Okay, thanks for having me. And then thanks for a nice introduction. So I'm Seok-Jun, postdoc at MPA. So today I'll talk about my recent work on radiative transfer effect in the hydrogen Balmer line in the little dot. So and then how this impact on the black hole mass measurement. So this work is with a collaboration with the Max Kronke, Yorit Matti, and Charlotte Mason. So first of all, let me start with the brief introduction about the little dot. This is an extremely compact red color galaxy discovered by the James Webb. So redshift is higher than 5. On the left, on the left, you can see the images of the little dot by James Webb. These sources are very small and red color. What makes them especially interesting is their strong hydrogen emission line. In particular, they show the very prominent H-alpha emission with the broad wing with the width of the over 1,000 km per second. On the right panel, you can see H-alpha spectrum from this object. This panel corresponding to the left panel images. So the combination of the compact size, red color, broad Balmer line make a lot of discussion about what power this system and then what make this line formation. So one interesting result is several groups have estimate black hole mass of the little dot. So their black hole mass is very high. So here the x-axis showing stellar mass, y-axis black hole mass in the two previous paper, recent paper. So the thing is the black hole mass and stellar mass ratio is much higher than local sample. Local sample means the AGN sample. So the key question is how to estimate black hole mass of the little dot. So usually people assuming this little dot is AGN, LRDs, AGN, and then using the standard approach, assuming broad component of the H-alpha originate from the broaden lesion in the AGN, just like local agent sample, and then so that broad wing is fit, and then with the luminosity of the full viscous maximum of this broad H-alpha component, and the black hole mass estimate by kind of empirical mass relation between black hole mass and then H-alpha things, which is come from the reverberation mapping of the AGN. So in other words, this black hole mass estimation like entirely on the interpreting the broad H-alpha component is coming from AGN broaden lesion. So another interesting feature is like, however, this is an alternative explanation for the H-alpha broad wing. So Thomson scattering, which is electron scattering. So Loud 2006 paper showing the electron scattering produce exponential wing profile on the emission line. This sample is NGC 403995 is also local AGN. So in more recent work show the exponential H-alpha wing in the little dot in the middle panel show that we can see the exponential fit matched the wing much better than Gaussian. So it tells us that broad H-alpha component is little dot may not be classic broaden lesion assumption. So it could instead produced by the Thomson scattering in if LRD have like the Thomson thick gas. Another interesting feature is like many of them showing absorption feature in the Balmer emission line. So roughly 30% little dot display the Balmer line absorption feature on the top of the broad emission wing. So in the left panel, for example, you can see so H-alpha, H-beta from one little dot GN97781. The both lines showed not only exponential wing, but also absorption feature. And then the spectrum looks like p-sigma profiles. However, in the center right panel, the Balmer lines still have absorption feature, while the partial line do not have the absorption feature. So this difference can be understood by the atomic physics, because Balmer line mainly involve like 2s 2p state in the atomic hydrogen. The level 2s state is kind of metastable state because 2s 1s transition is forbidden line. So 2s electron lifetime is much longer than other excited state. So this, which means other excited state like population much less than 2s state, only considering excited state, probably 1s state is always dominant. So for this region might be, so LRD have the only absorption in the Balmer line, not in partial line. So I will address this point with my simulation later. So another interesting feature, spectra feature, is like the V-shape V-shape SED. So this is very interesting. So because when we convert this the spectrum into rest frame, so the dip minimum of the V-shape is aligned with Balmer jump at roughly 3600 angstrom, so that this V-shape is from the strong Balmer jump. To produce such a prominent Balmer jumps, a dense optical thick gas is required for highly enhanced level 2 population of the atomic hydrogens, which with both Balmer absorption and then Balmer jump. So, but basically, I introduced like little dot people assuming as a AGN. So another scenario is like in the Naidu et al. 2025 paper, they propose little dot LRD is kind of black hole star. So they suggest that little dot is like composed of the massive black hole and then accretion disk emitting hot radiation like AGN, but there's no broad line. This accretion disk and black hole is surrounded by dense optical thick envelope. Based on the cloudy modeling, which is the photoionization codes, so they successfully reproduce like SED of LRD. So is also black hole mass measurement is much smaller than agent assumption, like the reverberation mapping based measurement. So this is also interesting feature. So also in this paper, they suggested another idea. So broad H alpha of the LRD originated from the H beta scattering in the optical thick H1 gas. So this is quite interesting idea. So in the left panel showing if H beta photon undergo many scattering similar to Lyman alpha behavior. So in the dense gas, so we can they say can reproduce this feature can reproduce like the H beta spectrum from LRD. So, but the thing is, even if like H beta suffers scattering like Lyman alpha, but this process is not like a Lyman alpha because H beta is not a resonance line. So which means like, so understanding that H beta feature in the LRD, so studying the Balmer line radiative transfer is crucial. So during this talk, so I had introduced like interesting spectral feature of the LRD. So the rest of my talk, I just want to address the three questions. First, there's a scattering of the Balmer line, especially for H beta, is actually similar to Lyman alpha. And then second question is, what role does Thomson scattering play? Electron scattering produce like exponential wing, also broad wing together. So that can be affect the black hole mass estimation. So another third question is another physical phenomena to form the broad wing around the Balmer lines. So I just want to suggest another scattering process. So basically to address the first question, so I modeled radiative transfer for Balmer line scattering. So here, left panel, you can see the energy level of the hydrogen. So usually Lyman alpha interact with ground state electron, but here in this code, so I assume like 2s metastable enrichment gas. So in the 2s electron interact with H alpha and H beta, But here I assume two things. First, the transition of the Lyman-series, which means the excitation to the 1s state is ignored, because probably this happening in the dense gas, so it's optical thick. So like the condition for case-free recombination, so which means we can say this on-the-spot approximation for Lyman-series is working well in this medium. And then secondly, we only consider 2s state excited electron due to its long lifetime. So here is the branching ratio for H alpha and H beta. So because H alpha excited electron from 2s to 3p, in the case of the H beta from 2s to 4p, so which means, so here I only consider 3p to 2s for H alpha. This is similar to Lyman alpha process. For H beta, I consider multiple branching to n equal 2 state and n equal 3 states. So this multiple branching so make H beta transfer differ from Lyman alpha. So to test this effect, so assuming monochromatic H beta source, in our the radiative transfer calculation, we found H beta undergo significant conversion into the Paschen alpha and H alpha line. So when the optical depth is higher than 10. So here left panel showing conversion rate from H beta to Paschen alpha through the n equals 3 state, so as a function of the 2s state column density. So we can see clear trend. The most of the H beta convert to the Paschen and H alpha. So when optical depth is higher than 10. So also this read directly different flux ratio and H alpha and H beta. So in the center panel showing variation of the H alpha H beta flux ratio. So it's increased dramatically with increasing the column density. Importantly, this high H alpha H beta flux ratio is arise without any dust attenuation. This is purely from radiative transfer effect. So due to the n equal 3 transition of the H beta scattering. So in the right panel, also you can see the resulting line spectrum for H alpha H beta transfer with Gaussian source with the width 200. So H alpha, as I say, H alpha transfer is similar to Lyman alpha. So H alpha formed the clear double picture like Lyman alpha, but in the case of the H beta, it's become more central deep. There's no double peak because like the scattered H beta compared to Paschen alpha and H alpha. So the key thing is like in the optical thick medium, so most H beta photon do not escape as a H beta. They get converted to the Paschen alpha and H alpha transition photons. So that in the simulation, we also tested the idea that H beta scattering alone could produce the broad H beta component. So is this working well? Looks like we do reproduce a wide H beta line without with our simulation. However, once we look at the really RT visual, the thing is, so the problem is in this case, so for after suffering numerous scattering, all H beta convert to the H alpha. So if H beta profile in the observation is come from if it is come from the H beta scattering, should be H alpha H beta flux ratio is much higher than 100. So which means in the observation, usually in the LRD, H alpha H beta flux ratio is like roughly 10 less than 10. So which means this H beta scattering scenario is hard to explain that observed broad H beta in LRD. So next thing is like the Thomson scattering. So let's switch the gear and just look at the Thomson scattering. So Thomson scattering is simply elastic scattering with the free electron because electron is much lighter than hydrogen. So in the normalized gas, electron velocity is much higher than hydrogen. So at 10 to the 4 Kelvin, the electron thermal motion is 500. So which means if photons occur Thomson scattering just a few times, easily make like broad wing, the width is over 1,000 kilometers per second. But the problem is Thomson scattering cross section is quite small. So because of that, so to make Thomson scattering, so the high electron column density is required. So I based on in this geometry, so composed of the central source surrounding electron gas, so I make the Thomson scattered feature for various temperature in the top panel. You can see the width of the Thomson wing increase with increasing temperature. I also measure full width half maximum of this wing feature. So there's a clear trend. So even if like the width is increased with increasing optical depths, but as a function of the temperature, the trend is just a proportional, width is proportional to the temperature scale, because this exactly represent thermal motion. But the main question is, so this can impact the black hole mass measurement. So as I mentioned earlier, so to measure black hole mass in the LRD, so people use a broad component. So for this test, so I assume like input narrow spectrum and then running Thomson scattering simulation and then get this escaping spectrum, this blue color, and then with the 2 Gaussian fitting, so I get broad component of this escaping spectrum, which is orange line. So, and then assuming H alpha luminosity 10 to the 42 arc per second, which is typical H alpha luminosity of LRD. So, and then, so using this black hole mass relation with the H alpha full width half maximum luminosity, I measure kind of imaginary black hole mass. There's no black hole, but we can measure black hole mass because we have an equation and then broad component of the spectrum. So here, so in the right panel, you can see the black hole, imaginary black hole mass as a function of the electron temperature. So you can easily indicate temperature is just roughly 10 to the 4 Kelvin. Optical depth is 1. The imaginary black hole mass is higher than 10 to the 7 solar mass. So this is a typical also black hole mass in the LRD. So which means if the LRD have Thomson thick gas, so that could make broad wing feature without broaden lesion in the AGN. So another scattering process is Raman scattering. This is quite interesting feature. So in the UV continuum near Lyman-series also can interact with atomic hydrogen. So through the interaction with the ground state electron, so this electron excited to the kind of the state between like n equal to 3 or 3 to 4 state. So and then de-excited to the intermediate state. So which means some scattering, Raman scattered Lyman beta photon can make the H alpha wing. In the case of the Lyman gamma, can make H beta wing. So for this feature, I also set up similar geometry, central source, and then spherical gas. So also this Raman wing feature, so observed in the many objects in the Stockholm region is by Dopita et al. And Henry et al. So also in the symbiotic star, also in the theoretical study, expect Raman wing in the AGN in the LRD. So also, so that to test the Raman wing formation in the LRD, so I set up this geometry. So this simulation with my previous course. So, and then I make the H alpha, H beta Raman wing, assuming like flat UV continuum near Lyman beta and Lyman gamma. So Raman scattering, as I mentioned, so Lyman beta and Lyman gamma form broad wing around the H alpha and H beta. So the width of the Raman wing in the right panel, you can see this is color represent different H1 column density. The width of the Raman wing increase with increasing H1 column density. So however, different from Thomson scattering, because Thomson scattering always makes same width wing around the various line, but in the case of Thomson scattering, so H alpha, H beta width is different. So in the central panel showing full width half maximum of the Raman wing as a function of the H1 column density. So each color represent different line, H alpha, beta gamma, and Paschen bracket line. So each line have a different width. So about the H alpha and H beta, usually H alpha broad wing Raman wing is like 3 times broader than H beta wing. So why it happened? Because the scattering cross-section of the Lyman gamma and Lyman beta is different. So Lyman beta have like higher damping time, and then like the higher oscillation strengths that make different Raman wing feature around H up and H beta. So I just back to question. So about the first question, so radion scattering of the Balmer line similar to Lyman alpha? Nope. Because of the transition to n equal 3 states, H beta transfer differ from Lyman alpha. So it make the additional partition in H alpha photon. So however, not however, sorry. So how does the Thomson scattering impact hydrogen line formation? So Thomson scattering can easily make broad wing with like that over 1,000 km per second. Also, Thomson wing provide kind of imaginary black hole mass, which is higher than 10 to the 7 solar mass at temperature 10 to the 4 and optical depth 1. So also another physical phenomena to form the broad wing, there's Lyman scattering, but Lyman scattering make different width of the wing, but usually in the observational data, so some H alpha, H beta wing looks like similar width, but we can say, so Lyman scattering can contribute wing formation, but this is not significant. So here's the brief summary of the future plan. So LRD, little dot, is super interesting. So, and then still like there's a lot of caveats because people really no idea this is agent or black hole star, whatever. So also I plan to combine Thomson scattering, radion scattering, so to reproduce observed emission profile. Also, I extended my RT code for H gamma involving partition beta line. So thanks for your attention.
Recording?
Or, well, either way.
Yeah. Thank you for exciting talk, and maybe it's time for a question.
Yeah, do some online and we can pause it later.
Happy to answer one. Yeah, great talk. So in any sort of realistic cloud or a set of clouds around the center of a galaxy, it's going to be a range of density, probably has a density profile. And so the radiative transfer in the dense parts is going to be different from the radiative transfer in the outer parts. And have you looked at how that, I mean, that might explain why we don't see factors of 100 H beta to H alpha, for example, but have you looked at some kind of a density profile and how that might affect interpretation of black hole masses or anything along those lines?
So now you mean like the density profile of the galaxies or other modeling?
Of the gas, right? So you're saying, okay, I'm looking at these line features and the Thomson scattering and so on as a function of density. But you know, in any realistic scenario, the density is not uniform, right? And so it'll have some profile.
Yes.
And so how would that affect, interpretation?
So also, I think basically in the, for example, ISM, CGM, IGM, so never make this high density, also never make highly populated n equal 2 state. That's clear. So, but in the both, like there's, in my opinion, like in the LRD field, there's a two big group, like some AGN people and black hole star scenario people. So both of them want to explain like the Balmer line absorption feature. In the case of the AGN people, they saying that broaden region in the early universe is more dense than local broaden region. So which means number density of the broaden region is higher than 10 to the 10. So that number density can make enrichment of the level 2 population. So that's one of the scenario. Another scenario is, as I mentioned, the black hole star scenario as their model is composed of the black hole and accretion disk and then surrounding that envelope. So that envelope number density is they usually assuming like from 10 to the 10 to 10 to the 12. But honestly, that black hole star modeling is very naive because they only assume H1 column density and then just radius of the cloud and then just running cloudy and then figure it out. Okay, this is at a SED fitting well. So they also trying to figure it out. So how do we set up realistic modeling? For example, so in this, like the gas condition is, and in the hydrodynamics, is it stable or not? Is it still caveat? So one of the postdoc at MPA, he now working on like the hydro simulation for LRD. So he tried to test like direct collapsing, so black hole can explain LRD. So because like if black hole direct collapse happen, so the lot of gas occurs into the black hole, maybe that makes some dense envelope probably. Even if like borderline lesions formed, not formed, but there's a dense envelope. Yeah.
And, yeah, I have a question. So it seems
Yeah.
like your theoretical works based on the observable observational predictions.
Yeah.
Pretty much these observational features are degenerate with multiple physical scenarios, but there seems like still some sort of differences out there. So do you anticipate any of the future observation can discern these physical different scenarios? Yeah, in looking at the line profile or something like that.
So for the, you mean like the scenario means like agent versus black hole star, or
Yeah. Or whatever the physical processes you mentioned
oh,
in this
that
work.
the one thing is like if the broad component is not from the Asian borderline, so maybe so in the case we can say something, this is not Asian at least, but we cannot say this is black hole star. So recently, so the one postdoc in East Vienna, so I was a co-author of the proposal. So he proposed like the polarized spectropolarimetry observation of the local LRD candidate. So to measure the polarization of the broad wing component, because if the broad wing is come from the borderline region, so it's unpolarized because it's just a kind of intrinsic emission process, but that wing is come from the Thomson scattering. So if the scattering region is not perfectly symmetric, so the broad wing should be polarized. So that is one of the method to break kind of which scenario is correct or not, but still caveat because like most of LRD is like observed observed by James Webb, so which means redshift is much higher than 1 or 2, so it's really hard to get a spectropolarimetric observation. I say maybe HW, we can figure it out, polarized feature of the H alpha, H beta from LRD. I'm looking for that.
Thank you. And are there any questions?
Good, great talk. And maybe just going back to Harry's question a little bit, I was looking back at your abstract that talks about these, it could lead to, black hole estimates that are overestimated by a factor of 10 or more. How likely do you think that is for a lot of the measurements out there? And like you said, it might be hard to find out, I guess, but
there is also different caveat. So I want to explain you a bit about the black hole mass plot. So because I discussed with many people about this plot. So what's the problem? So as I say, the black hole star people say, oh, maybe black hole mass is overestimated. But some high-Z people who work on the EOR or really high-Z galaxies, they say, I don't believe stellar mass measurement. Yeah, this is also one of the caveat. Yeah, so that took it like to estimate this, like the stellar mass, how people do like using some like the fitting stuff based on the local template and then estimate the stellar mass. Some people arguing, so we need kind of different SAD fitting method for LRD. Yeah, this makes sense.
Thanks.
I have just one quick question. So I think you have your own RT procedure to calculate these predictions, and then do you have any plan to publish it for people can use and generate their own predictions to fit with the observed spectrum?
So basically, currently I'm working with the URI to fit H alpha H beta spectrum by James Webb in that one object. So about my code, so initially I plan to publish it like library of the spectrum first. So, but yeah, I also plan to publish my code because here I used my previous code, not kind of recent code name is RTSCAT, is ready transfer for scattering. So this code can handle all scattering process, Thomson resonance kind of. So I plan to publish this code maybe at the end of the next year. So because I just changed my position last month. So that position goal is kind of like developing some public radiative transfer code for ionization and then Lyman alpha radiative transfer. Maybe that code include a package for like the Balmer line transfer. But now I'm just focusing on the physics of the scattering process because now I only consider H alpha and H beta. So I plan to extend it, as I mentioned, for H gamma. And then in the case, I can generalize this problem, and then which means maybe can handle multiple Balmer transition, because the line difference of the H alpha and H beta is matter. So not only galaxies, also many stellar people, many stellar objects show different H alpha, H beta spectrum. So I plan to adapt this code in generally for not only for LRD, it's only also for like stellar object like T Tauri star or symbiotic star, kind of that.
Thank you. And yeah, I mean the current predictions seems already interesting. So publishing the line profile libraries with the parameterization would be useful for observers to fit their spectra. Yeah.
Yeah, maybe that library include like the fitting tool.
Yeah.
That's a plan.
Yeah. So one more question. This is going back to early part of the sort of review part of your talk where you talked about the V shape and you mentioned the sort of inverted Balmer breaks.
Yeah.
But so are there any that show an actual Balmer jump or is it really just the V shape?
No, it's just actually this red dashed line represent like wavelengths of the Balmer jump.
Yeah, it's just that I've never seen one like occasionally in galaxies you can see an actual jump as opposed to just an inflection. And I don't know if that's seen and then the spectrum isn't like continually rising from that effect. It has a jump and then it falls off again. So I'm not sure how the sort of Balmer jump explains the V shape per se, right? If I saw a jump, ubiquitous jump, I'd say, yeah, that's pretty convincing, but I'm not sure I know of any red dot that has a jump there.
Yeah, that's true because because here it looks like have a V shape, so it's like not a significant Balmer jump. I agree. So because most of the fitting stuff, so I'm just talking about the fitting, not about the physics, like the fitting stuff. So how they fit this like V-shaped spectrum. So they put in some kind of stellar spectrum with the Balmer jump, and then additionally putting the SED for the star-forming galaxies. So which means like clearly this total SED does not have clear the Balmer jump. So, but another interesting scenario about this V-shaped SED. So as I mentioned, so basically, firstly, people detect the LRD with the broad H alpha line. So that obviously people think that this is HN, but there's no IR axis and then also rag of the X-ray luminosity. So people starting like have a curiosity about like the what is this kind of that. So and then people trying to figure it out how, but also H alpha H beta flux ratio is much higher than KCB expectation. So people saying, oh, maybe dusty. Also red color, people easily saying this is dusty. But if there's a dust, it's impossible to understand like the UV axis and the UV radiation. So I'm saying Yeah, so I don't know if this is really Balmer jump or not, but it's probably someone to figure it out. Now the you're working on try to find the correlation between Balmer jump strengths versus absorption line strengths of the H alpha and H beta. Maybe that study would be to figure it out. This features will be Balmer jump or not. Some spectrum does not have absorption but have a V shape. Maybe this is not from Balmer jump, but clear absorption line with Balmer jump, we can say there's an enrichment of the level 2 population.
Yeah. Yeah.
Thanks for a nice question.
Yeah. Yeah, thank you so much again. And
Yeah, thank you.
yeah, I will stop recording for now.
Oh, I just wondering, so next year, so June, so there's the MEAP workshop for James Webb in Munich. So anyone interested in that, or anyone who will come to Munich, just to let me know.
Great, thanks.
Yeah.